So I want to go over a concept that I forgot to go over when I was going over spectral angle mapper with you guys a couple classes ago. And it's really one of the, spectral angle mapper, as we described it, was a technique very similar to minimum distance and a mean, except you're working in an angle space. And its biggest advantage, or its biggest proposed advantage, was the fact that it can still do a good job at identifying a material when the material is under different illumination, right? So if it's in the shade, it's just receiving skylight, or it's in the open, it's receiving sunlight, it'll still fall along that same vector. So any angle between any unknown pixel that's part of that class and that class itself would still be small, regardless of the illumination, right? So that's what it was proposed to be, and it is that, right? So, but let me propose something to you where it's going to have a little bit of a problem. All right, so this is the side of the building, and we have the ground here. And let's say the ground is grass. So we have grass coming up the side of the building. And let's call it grass. And let's call the side of the building here brick. All right, now let's put the sun over here. So we get a shadow that forms in here. So this area is shadowed. And this area out here is exposed to the sun. All right, now the hope was that if we were to look in, let's just go in two space and look at let's just look at two of the bands in this case. And if we were to plot a vector between band 1 and band 2, this point right here would be the band 1 digital count, band 2 digital count. Right? So that two-space position would show the position of that vector in two-space. And if I were to look at a point here out in the sun and a point here shade, then the premise was that that point would fall, the one in the shade might fall here on the vector, and the one in the sun might fall here at the end of the vector, right? But they all fall on that same vector. All right, now let me ask you a question. As you start to get closer and closer to this building, right, to this brick building over here, what happens? Scatter from the building. What's that going to cause? Right. So now you have inside the shadow area you have skylight coming down and illuminating that area. Right. It's going to have a certain color to it. Right. That color, that source power distribution, is going to be different than the source power distribution from the sun. Okay. So if I were at this point right here, way out near the edge of the shadow, I'm going to have a particularly heavy blue source power distribution in the visible portion of the spectrum, as opposed to the sunlit portion, which is right here, right? So just outside that shadow, the color of my light, the source power distribution, is going to significantly shift, and you're going to get more, you're going to peak more in the green, right, where the solar power source distribution peaks. Right, so you're going to get a shift in the illumination. As you get closer and closer to this building, you're now going to get another shift in illumination, right? Because some of this skylight is going to hit the side of the building and be reflected down onto the target. Right? So if this brick is red, you're going to get a significant increase in red photons hitting your target. Okay? So you're going to shift from a primary, most heavily green illumination out here to a very blue illumination here, and you're going to transition to a more red and red illumination as you get to here. So what is that going to do to a spectral angle mapper? right? All of a sudden, you're going to have this big old envelope of places where that vector might fall from this graph's target, because the source power distribution changes very significantly. So that's one of the downsides of spectral angle mapper that you've got to be very aware of. People use this, and all they do is they read Joe Boardman's paper and say, hey, this is supposed to work great inside of shadows. But if you think about it very carefully, it shouldn't work at all well inside of shadows, right? Because of this change in illumination. All right, now to be fair, if you look at the original paper on this topic, they talk about satellite-based imagery, things like Landsat. We have 30-meter pixels. Number one, do you see shadows like we're talking about here in 30-meter pixels? Right? You don't see shadows from sides of buildings, they're just too small. I mean, very large buildings you might start to see them, but generally you don't. But if you're talking about the sunlit side and the skylight lit side of a mountain, sun's still low in the horizon, it's illuminating the east side of the mountain, the west side of the mountain's still dark. The land cover types on both sides of that mountain could very well be the same. Right? And you still have this coming into play because one's primarily skylight, one's primarily sunlight, so there is some shift. Right? But this cone is going to be much narrower when you're just talking sunlight and skylight, as opposed to bringing in scattered light from the sides of other objects or adjacency effects from other objects in the scene. So it doesn't, I mean, even in the most perfect case, as described in the original paper, it doesn't work as advertised because the source does change. So it is a little bit better than minimum distance to mean because it is a little more robust to it, but what I want you to do is always keep in mind this fact that it does fall apart when the illumination changes. Now, that being said, I've used Spectral Angle Mapper on all other kinds of applications. I'm currently using the Spectral Angle Mapper right now to classify down to the species level dragonflies based on the venation patterns in their wings. Right? So every dragonfly, their wing, every species of dragonfly, their wing is unique to the species. And there's, you know, they kind of look like this. And over here, in every dragonfly, there's just kind of a triangle region that forms from the veins and wings. Sometimes this might be broken up into little sub-triangles also, but there's this dominant triangle over here. There's a length-to-width ratio that's indicative of species. There's this really heavy vein that falls up here on a dragonfly wing that's of different lengths and different thicknesses based on the species. And right now, I'm actually using all these features: the area of this triangle, the base-to-width ratio of the triangle, the base-to-width ratio of the wing, the length and thickness of this guy over here, this heavy vein on top. And I'm using Spectral Angle Mapper as a classifier, because it works really, really nicely in this case. It's really fast. But I don't have any other problems. I don't have illumination changes or anything like that. These are just features that are not based on illumination. So it is actually working out very nicely in that case. So don't throw Spectral Angle Mapper away totally out of your toolbox of things that you use for classification. I would say be very careful using it on remote sensing data, where we're teaching it to you, right? But be very open to using it in some other situations because it is very, very quick to compute. And it works nicely in situations like this. All right, so I didn't want to leave Spectral Angle Mapper without saying that. So just keep those things in mind. All right, now I have a topic to talk about today, but I want to, which is feature reduction. But I want to make sure we have enough time to answer any questions on things you might have for the end of the exam, anything we've gone over in the course, you know, anything you have. So why don't we do that up front, and then we can look into this topic as time permits.
Is there any way you could post that Excel document that we were using for the contingency tables? You know what?
Oh, the one I use in class here.
Mm-hmm.
Yeah. Yeah.
send me an email?
Yeah, I was going to say, can somebody send me an email and remind me to do that? Because I got to head for the airport right after class. And once I get over to the airport, I'll post it. But I know I won't remember it between security and getting on a plane. Right, so, yeah, if you could send me that, that'd be great. All right. Anything else?
So if there were to theoretically be a derivation on this exam, where would we be looking for said topics for a derivation? I'm not saying there is or isn't. I'm not saying you have to tell us what it is. I'm just saying, because I'm not sure that we've really gone through any particular derivations in class, and I don't think I saw anything
I think
huge in the book, so I just thought I'd ask.
There's nothing on this exam that's,
okay.
that's you know, that lends itself to that particularly. Besides Gaussian maximum likelihood, the equation, the driving equation, right? I mean, that leads itself nicely to a derivation.
Okay.
So that would probably be the only one. That's been on the it's been on the comp in the past. So if you're looking to take the comp sometime in the future, the derivation of Gaussian maximum likelihood has been there. I'm sorry, Greg. The question was, if there was to be a derivation on this exam, what might that derivation be? And I think since the last exam, the only thing we've done that would lend itself to that is the derivation of the Gaussian maximum likelihood.
I didn't understand what the takeaway was from Garlick's texture.
Okay. All right, so we've been doing a lot of classification, and all we've been talking about is spectral bands. And that is, if you go back and you look at what we did way back in chapter 1 probably, when we were looking at the photo interpretation cues, I mean, only one of those cues was brightness, right? But there was lots of other cues there. One of them was in fact called texture, right? Then there was one called pattern, right? Those two in particular are observables that you could, when you're looking at a scene, sort of converse through and describe to me, right? And in your visual processing, when you look at anything, it's part of the decision processes that you make, right? And you see textures, and you know, you can tell if something's a fabric or a painted wall. It might be exactly the same color, but if it's a cotton material as opposed to a painted piece of drywall, even if it's the identical color in all the wavelengths that you could see, you could still tell the difference between the two. And that's probably because of the texture or the patterns that you're seeing set up in that material. So the takeaway is that we don't use that information typically when we take an image data source and we run it through a classification scheme. Right? We usually just use the spectral information. Or we might transform that spectral information into principal component space and use the principal component information. Right? But it's still just information derived from spectral data. The idea from Herlich is to generate these features and add them to your image. So if you have a 10-band image, and you generate 15 Herlich features, add those features to the image, make your image cube larger, have a greater depth, and use that as part of the classification process. Right? So what are you doing there? You're not really looking at it in a global sense where you see a texture pattern and you know it's cotton or whatever sort of material that you may be looking at, or you can see this carpet. This carpet has a very distinct texture to it, and probably if all I showed you was a patch this big of that carpet, my guess is very quickly you would tell me that that's probably a piece of carpet. Right? But you didn't do that from the color, you did it more from the texture, and you did it more from looking at the entire scene. Right? At a per pixel basis, what Herlich tries to do is tries to quantify what you see in a global scene. So that's a very difficult thing to do, and Herlich features do a fairly consistent job at it. And I want to be a little cautious in what I say there. Because I don't know how I would even describe texture, right? And then how I would think on a per pixel basis how I would give you an indication of that. And I don't think Herlich did either, right? Herlich just started computing these things called entropy and you know, sum squared variance, and these were all just statistics. These are just numbers, right? They happen to correspond if you look at them. Bright portions of the image, you can easily go in and say, oh, well, okay, the bright portions, that's where the gray levels are changing quickly. And to that level, I think they're indicative of the texture that you see. But I don't want to say that they're describing a physical quantity called texture, because I don't know that I can even do that in words. Right? So to come up with a metric to do that, I think is very difficult. So what Herlich's features try to do is try to bridge that, try and split the difference between a really good conversational description of what a texture is, all the way to spectral bands. Let's split that difference and let's try and say, you know, I have something here that correlates well with what you interpret to be different textures in a scene, right? Some of those features, if you look at trees and you look at asphalt, right? Asphalt tends to be fairly smooth, trees tend to be very, or have a lot of small contrast changes over very short distances. Some of those features are bright in one area and dark in the other. So there's a correlation between those. And it's that correlation that the Herlich features try to set up. And it's just the same correlation as an object having a big reflectance in one wavelength and a lower reflectance in another wavelength. It's just a correlation in how much energy is reflected. So the Herlich features are just that. They're additional bands to add to your image. To hopefully get a better classifier. And every time I've added Herlich features to my classifiers, I have seen increases. So I don't know which ones to tell you to pick, right? Because that depends on the actual the image itself. But this concept called feature reduction might in fact just do that, which is the last topic I want to cover.
So how do you, just to get back to that,
Yeah.
how do you decide, okay, to use the example of the cornfield, how do you decide what your road should be, or like the distance? Like, I mean, without looking at and deciding, okay, well, I see that there is a
10 pixel spacing between each of the rows of the cornfield.
Right. I mean, you know, an algorithm isn't just gonna, without looking at it, no.
Right. No, I totally understand what you're saying, and the answer is most of the time we just say, let's take the defaults inside of Envy and see what it does. Right? Not a good answer. The only way to really do that for sure is to look at that image and say, hey, that's a particular feature. I'm doing an agricultural study. I want to make sure I get cornfields separated from soybeans. Let's assume they look different when they're planted. So in order to do that, I want to have a feature, a Herlich feature come up that will take the texture that I see in a soybean field and make it look very different than the texture I see in a cornfield. So let me look at my image and say, okay, that's roughly 10 pixels apart, so I need to take my distance parameter in the Herlich features in that co-occurrence matrix, and let's make that 10 as opposed to 1. Or let's make it 5 if it makes sense to get a bright spot, a dark spot, a bright spot, you know, sort of a sampling theory sort of approach. So it has to be image dependent.
And that makes sense on the application of what you're actually looking for and the conditions in which you took the image, like how high were you? And
Right. Oh yeah. I mean, if you're at a different altitude, that spacing is going to
Right.
be different. Now, an automated approach to that might be to take the Fourier transform of that image and look for some spikes in the frequency domain representation that might represent some sort of a sinusoidal change in a particular direction. So if the cornfield is oriented north-south in the image, I think the spikes will appear along the u-axis in frequency space, and if they're east-west, they should appear on the v-axis. If they're oriented on a diagonal, you'll see them off those axes. Right? So if you have you done this in DIP yet? Have you done Fourier analysis of imagery?
We talked about a little in vision actually, with the sharp edges and stuff.
Okay, but you've seen two-dimensional Fourier transforms of, let's say a two-dimensional sinusoid, you see the Fourier transform, you see a double delta sort of function. Okay, so you'll see that sort of thing if the cornfields are a dominant enough feature in the image to have the power and the frequency domain be significant enough that you can actually visualize it above all the other information that's there. Right? So you can start to use that, right? Because you know if you see that double delta has a certain spacing in the frequency domain, you can translate that back to a spacing in the spatial domain, right? through delta x and delta u, right? And then you could decide on the distance metric in a semi-automated fashion, perhaps.
So all that is going to be included in this test is classification, or are we going to cover more than that?
Well, what we did classification, we did PCA,
Right.
M&F stuff. We did something right after the last test, also.
What's
The minimal noise fraction.
Oh.
We talk about some spectrals moving or image restoration, which I don't know.
Yeah, we talked a little bit about the direct inverse filter and the Wiener filter, but we didn't go very deep into that. And you'll see that again next quarter in image processing.
So
My guess is
later
you'll
to-
see it. You'll see that on a test at that point.
Alright.
We used shot slides for contingency matrices, right?
What's that?
We used Dr. Shot slides for contingency matrices. It wasn't in any of your ones.
I did not have that in any of mine.
And was just, get the slides from chapter 14, 15, 16,
And 17.
Yeah, 14, 15, 16, 17.
Is it worth putting anything from the last test on our cheat sheet? Like those different methods, right, to make that equation wise?
I don't think so.
Brett was asking to repeat the questions.
Oops. All right, so I remember the questions now. One of them was which slides from the BIP class would be on this exam. That was slides 14, the sets 14, 15, 16, and 17. Was there any of the equations from some of the atmospheric correction techniques that were on the last test that should be on your mind for this one? And I would say no. Too bad.
Or not be caught when you said classification, PCA, and MNF?
Classification, PCA, and MNF were the primary topics. Yes, there is a cheat sheet on it. One page of notes, just like last time. I hope you knew that last time. And then there was a question of whether or not the image restoration materials would be on this test, and the answer there was that you'd see that again in DIP. And that's where you'd probably see a test on it.
The test still worth 30 points?
Yep, our first test was 25, last one was 30, and this one will be 30. So 85%. All right, well, if you think of anything, blurt it out. All right, so the last topic, like I said, what I want to do is go through this thing called feature reduction, or you might hear the topic referred to as feature selection also. Man, I didn't get very far. Go ahead.
I'm sorry.
It's okay.
When I did the contingency matrices in NB, they didn't add up to 100 on the bottom and on the right. They would add up to 100 on the bottom, and then they would add up to a different percentage on the right.
They transposed them.
But when we were,
I mean,
okay.
most of the statistical texts that you'll read have the marginals add up to 100 on the right-hand side.
right.
In NB, it looks like they transposed the matrix. And if you're an IDL programmer, the world is always transposed in IDL because it's a column major language. So arrays are number of columns by number of rows, as opposed to languages like MATLAB and C, where it's the number of rows by the number of columns. My guess is when they implemented it in NB, they implemented it according to the paper and it came out transposed.
Because it seems like we were saying that the columns are actually classified in, right? Or like that's the truth is the column.
Yes, the rows represent the truth. So you have to have as many pixels, you have to add up to 100% of the pixels in a truth row.
Okay.
So
So training data on the left.
Training data on the
Okay. And then an NV training data is on the.
right. Okay, yeah. So if you're looking at the contingency matrix, and what's labeled on the left-hand side is the ground truth classes. What's labeled across the top is the classes that the classifier classified pixels into.
Mhm.
What did you call feature reduction? Is that also called?
It's also called feature selection. All right, so there's two ways you can think about this. I have a bunch of features to look at. Spectral bands, texture features, you name it. I could then reduce the number of things that I'm going to use. Right? And that's what we were doing in PCA. Right? We computed PCA to say, hey, can I transform this data set in some way that I can reduce the number of features that I use in any subsequent analysis that I do. Another way to go about it is to say, all right, I have all these features. Which ones should I select in order to get the best answer? So what I'm going to go over here, I probably feel more comfortable labeling feature selection than feature reduction. But it's labeled feature reduction. Right? But I think you'll see that as we go on, that this will be more of a feature selection methodology. All right, and the reason you want to do this is twofold. Number one, if you have lots and lots of features and you want to do some sort of processing after the fact, the cost of classification, if that's the processing you want to do, goes way up with the number of bands that you might have. It's a lot harder to compute inverses of much larger matrices, just computationally. It takes more time. It's also much harder to choose training data to train these very large matrices, because you need lots of points in order to get a robust representation of those descriptive statistics, like the means and covariance matrices. So you want to, if you can, come up with the most efficient data set possible that's going to answer the question the best that you can. Right? So you don't have to send down a lot of data. And you might even think about that if you have a spaceborne system, and let's say it is a satellite that you launched and it's heading off to Mars. If you're then going to fly over, through the Martian atmosphere and do an observation of the surface of the Martian planet, then you have to get that data back to Earth, right? So transmitting data from Mars to Earth takes power. Operating a sensor and having all its, its whole payload operating takes power, right? So if you can conserve power on one or both ends, then you could have your mission last longer, right? So let's say you have 12 sensors on some probe that you have orbiting Mars, and one of those sensors is a hyperspectral scanner. It's collecting 200 spectral bands. One of the things you might consider doing is doing a little bit of onboard processing to say, out of those 200 bands, maybe I can do a PCA and only send back 4 bands to Earth. and that might have 98% of the information. So now I just save a whole bunch in my transmission power budget. Okay? That would be good, because now you can do several more revolutions around the planet and still have power to do that. But there's a trade-off you do there, right? To do onboard processing takes power. So you have to look at that entire budget. But it probably never hurts in any case, if it's a situation like that where you're power limited, or if it's just everyday sorts of remote sensing where you're doing classification after classification, it saves time in your life, right? If the processing can go quicker, or maybe you can get more done. So being able to pick out the best features is a very good tool to have in your back pocket. That's what I wanted to go through here. All right, so the cost of minimum distance to the mean and parallel pipehead type classifiers, these were very straightforward. These were compute a Euclidean distance, see whether I'm between two bounds, for a particular band. As you increase the number of bands there, the computational speed of these kind of algorithms tends to go up linearly. Okay? When you start to do something like maximum likelihood classifiers, which most people tend to use, that same increase in the number of bands causes a quadratic increase in the runtime. Right? So that's why keeping these things to a minimum is good if you can. All right, so there's many ways we can do this, right? There's two primary methods. One's direct elimination of features that do not contribute to the power of the classification scheme. Right? And that means take my original data set. Let's say I have say I have Landsat, so I have Landsat band 1, 2, 3, 4, 5, and 7, the reflective bands of Landsat. If I have those 6 bands, I might say, you know what? I know band 7 is not important, so I'm just going to throw it away. That's one methodology to use. The other one is to do a PCA on it and create a new transform set of data and use the ones that explain most of the variance in that data set. That's another method to use. So we've already gone over number 2 here. So what I want to do now is, how can we best do number 1, direct elimination? Right? Probably the answer is not for you to say band 7 is not a good band, I'm just going to throw it away. Right? Unless you know that. Unless you know something physical about the process, and you know something physical about the sensor itself, and you have a very good quantitative reason why that would be the case, you just making a blanket decision probably is not the best idea. It's probably best to let the data talk and decide from the data, let the data decide which bands are most important to identifying the classes that I want to identify. So if you grab a scene and you say I want to identify 3 different species of trees in that scene. Well, you might, because you're a forestry person and you've been doing forestry for 20 years and you've looked at lots of data in the past, you might say, you know what, bands 4, band 3, and band 2 are the 3 that I want to choose, because I know those are going to work the best. And experience is good, and that's fine. You can go ahead and do that. Or you could say, let me say I want to identify these 3 species of trees, and here's this data set, give it to an algorithm, and let the algorithm tell you which 3 bands out of the 6 reflective bands are best. Right? It might come back and say bands 4, band 3, and band 2, just like you did. But it might come back and say, you know what, band 5, which is a little bit further out in the infrared, so it's a little bit higher on that green edge, or the chlorophyll rise, that one's going to give you a little bit better classification accuracy. And it might say pick bands 5, 3, and 2, instead of bands 4, 3, and 2. Well, the data actually said that it was more separable if I used those those bands rather than the ones you chose. So why not listen to the data and choose those? Right? So even if you have lots of experience, it makes sense to run these kind of things to take a look at your data and make sure you're picking the best ones. It also will give you some sort of an indication of whether or not the ROIs that you picked are good. Right? If you can't get good separation between elm trees and oak trees and maple trees with the ROIs that you picked, then maybe you didn't pick your ROIs all that well. It might be that you can't separate those things because they're spectrally too similar with the sensor that you're using. That's a total possibility. But it might be that you just picked poor ROIs. And if you can use this sort of an approach during your selection process, then hopefully you can pick out a better set of ROIs and get your job done. All right, so if we go back to this concept of overlap in classes, so let's look at a two-dimensional case here real quick. If I have band 1 versus band 2, and I have a set of points that make up one class and fall here, and I have a set of points that make up another band that fall here, or another class that fall here. So this might be omega 1 and omega 2, two different land cover types. If I were to project this data down onto the band 1 axis and form histograms, right, I would get a histogram. Let's see, E is here. I'll make it a histogram that looks like this. And if I project this one down, it's right here. You might get a histogram that looks like that. All right, now, if I did the same thing on the band 2 axis, I might get a histogram that looks like this. And let's see, this one's pretty narrow. So I'll make it a histogram that looks like this. All right, so if those were your only two choices, those two bands, which band would you pick? Yeah, band 2, right? Because you've got no overlap. You have nice separation between these two classes in band 2. Right, so this overlap region is the problematic area, and that's where you get confusion. So what you'd like to do is minimize the amount of overlap you have between classes. Right? So the whole idea behind selecting the right bands to solve your problem for your particular classification scenario that you're talking about is to pick the right bands, the ones that have the least separation. So these two, for omega 1 and omega 2, are better than these two for omega 1 and omega 2. All right, so if we could do that, I think we'd be in good shape. Now, obviously, real data never looks as clean as this, and there's always going to be overlap, so the idea is trying to minimize that overlap. All right, so one needs to be able to separate or quantify this degree of overlap. And if we can do that, we'll define this metric called separability. And if we can define that metric called separability, and we could maximize the separability between classes based on our choice of input features or bands, then we'll come up with the best set of data that we can to perform the task that we want to do. So the problem here is, which bands do I pick to be able to separate these n classes in a scene, right, as best as possible. All right. Distance between the means is obviously not enough, right, because we have variance in our data. So we have to take into account that overlap, or that statistical distance measure that we've been talking about. So we have to incorporate variance or standard deviation into this somehow. All right, so let's take a look at some of this. All right, now, the first one that I want to look at is a concept put forward by in a textbook called Quantitative Remote Sensing, I believe was the title. It was by, the authors were Swain and Davis. You can see this textbook referred to in all kinds of texts. Schott refers to it many times in his text. It was put out in 1978. It ran one edition, and it's almost impossible to find anywhere. I found one on eBay about 5 years ago, and I bought it because I never had a version. If you ever have a chance to find this book, you'll find it. Somebody will be selling it for $10 on eBay. It's a really good book to pick up because everything refers back to this textbook. And they came up with this concept called divergence, back in their text in '78. And what is it? Well, it's a measure, like I said here, it's a measure of separability, or it's a measure of the degree of separability of a pair of probability distributions based on the degree of overlap. All right, so if I have class omega I and omega j here, and they overlap by this much, intuitively, if I push this omega j distribution to the right and this omega I distribution to the left, the degree of separability would go up. Right? And if I push them closer together, the degree of separability would go down. So the way they decided to measure this is using something called the likelihood ratio, right? Which is just the ratio of two probabilities. Right, so if we look at this is the probability of x given omega I. Right, so this is the multivariate normal distribution, assuming we have normally distributed data. And this is the probability of x given omega j, so two classes, so omega I and omega j. This is the likelihood of the ratio at a position x. So if I chose x to be right where my pointer is, I would take the ratio of the probability on the green line, omega I, to the probability on the red line, omega j. Now, that's going to be a number between 0 and infinity, right, depending on which way you take the ratio. Right? And you want the number to be near one of those extremes. Right? You want that number to be either some number divided by 0 or 0 divided by some number. Right? Because that would say these two distributions do not overlap one another. Right? If you have anything that's in the middle, that means there's some degree of overlap between the two distributions. So you'd like to see as little as you can. Now what we're going to wind up doing is not just looking at one digital count value, we're going to look at an integrated version of this likelihood ratio eventually. And we're going to be able to measure the degree or the total overlap between two probability distribution functions, right? Rather than just looking at it one particular digital count value. But we'll get there in a sec. All right, so this concept of likelihood ratio makes sense? This likelihood ratio between band I and band J given I have a pixel at position X. Okay. All right, so it's typically common to take the natural log of the likelihood ratio because most of the time we use this with a Gaussian normal distribution and there's an E in there and they like to get rid of the E. Right? So that's why it's common to do this. There's no other good reason to do that. All right, so we'll represent that quotient on the previous page, that likelihood ratio, which I labeled L sub ij. We can represent that here as L prime sub ij, which is the natural log of the likelihood ratio. Okay. And what does that do? Well, I can take that fraction that I had on the previous page and represent it as the difference of the likelihood ratio of the numerator and the denominator. So just rewrote it that way. Now, divergence, as defined by Swain and Davis in their text, was the expected value or the average likelihood ratio for all pixels x, given I have class omega I, plus the expected value or the average of the likelihood ratio for all pixels x, given that I have class omega j. Right? Now that expected value of that average is just going to be the integral over all possible digital count values, over all possible x's, in a multivariate sense, right? Because this is a vector, this x, of that likelihood ratio, the natural log of the likelihood ratio, times the probability of that particular event occurring, given I'm looking at class I. Right? So what I've got written here is this term, right? And you can equivalently have the same for this term. So you have two integrals to compute. And essentially, that's pretty easy. You're just going to go ahead and compute between I and j the likelihood ratio at a particular value x. You know the probability from your multivariate Gaussian normal distribution for x occurring given you're looking at class I. And you just take the product of those and add them up across all values x. And then you do the same thing for the likelihood ratio of ji, right? But you would replace the class conditional probability here. This would be p of x given you're looking at class omega j. And the sum of those two, the sum of those two likelihood ratios integrated over all wavelength values is what they call divergence. And the larger the divergence, the bigger that number, the farther those two classes are apart from one another. All right, so I can go through and derive all this, but divergence, like I said, was the expected value of the sum of those two things. I could substitute in the integrals, expand out what those integrals would look like, and then I could do some rearrangement of terms. What I finally wind up with is this equation down here, which is the difference between the two class conditional probabilities, right? For any probability distribution function, we're going to wind up using Gaussian maximal likelihood here eventually, but this would work for any probability density function times the natural log of that likelihood ratio itself. All right, so let's keep that in mind. That's what's defined as divergence. And it's a measure of how far two classes are apart from one another, given their probability density functions. And those PDS could occur in n space, right, depending on how many bands you have. So that's why these are still vectors, these x's. All right. So what are some of the properties of that equation? Well, it's always positive. Right, so we don't have to worry about signs. It's commutative. The divergence between class I and class J is the same as the divergence between class J and class I. Right, so it doesn't matter which order we do it in. If the probabilities are equal for all x's between the two classes, that means the two classes are essentially have exactly the same probability density function, then the divergence between those two classes is 0. So in other words, if I have two identical probability density functions and I compute the divergence between them, well, there's no divergence between them because they perfectly overlap one another. Right? So if you plugged in the case where all of p of x given omega I equals p of x given omega j for all values or all digital counts, if that was the case, then the divergence would come out to be 0. Which is good. It's a good feature to have here. If our features, our bands, are statistically independent from one another, right? And meaning that each digital count, each adjacent digital count is statistically independent from the digital count next to it. Right? And in the case of a probability density function, that's probably true. Right? Spatially, that's not true. If you know the color of one pixel, you make a pretty good guess at the pixel next to it, but that's not what we're talking about here. We're talking about the individual spectral components inside this probability function being independent from one another, and that's an okay assumption. Then we can come up with that class conditional probability by just doing the product of the individual probabilities of each of the bands. Right? That's not a big deal when it comes down to using it for what we want to do, but it is one of the features. But really the most important one, I think, is this last one, is that if I have n plus 1 bands, right? So if I have 10 bands, the divergence from 10 bands is always going to be greater than the divergence from 9 bands. So by adding more data, my divergence is always going to get greater, right? So if you think about that, in 2 space, I have 2 clusters that are separated, right? If I add a third band, I can't decrease the amount of divergence that I saw with just 2, right? Because they're going to be separated. If I add a third, they're going to get further apart or they're going to stay the same, but they'll never get closer together. So adding more bands always helps. I don't know if you've ever done, when you took your your basic statistics class, if you were trying to make a predictive model, and you were doing linear regression to come up with a prediction for something that you were looking at. You know, for instance, if you were trying to figure out the average SAT score for an RAP student, right? And you base that on the age that they took the SAT at, the city that they lived in, the average household income, and their favorite color M&M, right? The first 3, you probably could agree that they had some relationship to what the SAT score might have been. Favorite M&M color? Probably doesn't. But if you added the favorite M&M color, your R squared is going to go up. Right? It'll always go up, because you added that little bit more of information. It's the same sort of a concept that's occurring here. All right, so that I think is the most important feature. So keep that one in mind. All right, so the way that we would do this now to compute the divergence is to go back and take this equation right here and substitute in for it the Gaussian, the multivariate Gaussian normal distribution equation. Right, so I would put in here, you know, all the terms, e to the minus the Mahalanobis distance, or 1/2 the Mahalanobis distance, pre-multiplied by a fraction that had a scaling factor in there that was proportional to the determinant of the covariance matrix. That whole equation that we had previously. I would put that in for each of these things and go ahead and reduce it. Okay. I didn't do that. Here's the answer. Right, it comes out to be this. Swain and Davis do this in their text if you wanted to see it. It goes on for pages. All right, but essentially what it comes down to for a Gaussian maximum normal distribution, Gaussian multivariate normal distribution, this divergence comes down to this. 1/2 the trace of the product of the difference of the covariance matrices between the two classes times the difference between the inverses of those covariance matrices plus 1/2 the trace of the product, the sum of the inverse of the covariance matrices times the square product of the difference between the means. Right. So if you look at this sort of looks like a normalized distance. Right? You have distance between the two means, right, squared, divided by the covariance matrix, or the sum of the covariance matrix between the two classes. Right? So this is a normalized distance measure. This is, you know, something akin to a multivariate z-score. Right? It's not it exactly because you're using the sum here, but it's similar to that. So it measures the distance between the two means normalized by the spread of the data. And so this kind of has a nice distance feel to it. This one is only covariance matrices, right? It's the difference between two covariance matrices divided by the difference between two covariance matrices. That sort of has this feel of the spread, that, you know, that spread penalty that we're looking at in the maximum likelihood equation, where we're looking at the determinant of that covariance matrix. If you look at this one, we're taking the trace of it. Right, so we're adding up the major diagonals of this quotient. Right, so we're looking at really just the individual differences between class variances along that major diagonal. Right, so this gives us some idea of the relative spreads between the two data. All right. So, and we're looking at this just for a pair of normal distributions. Right, so this is for two classes only. So for the case where there are more than two classes, what we would actually have to do is we'd actually have to go in and compute all these divergence values for all possible pairs. So let's say I was looking at 3 classes. I wanted to do, like I said before, maple trees, elm trees, and oak trees. I wanted to separate those 3 classes from one another. I'd have 3 classes. So what I would do is I would compute the divergence between maple and oak, between oak and elm, and between maple and elm. Right? So I'd have 3 possible pairwise combinations to look at. And obviously as the number of classes go up, that number of pairwise combinations go up also. So what you would do is you would compute this divergence for all possible classes, and then somehow you got to make sense out of that. Now at that point, you could wind up with what's called the divergence matrix, which I don't have in the notes here. Okay, but you could imagine you have a divergence matrix here, which is the divergence between band 1 and itself, between band 2 and band 2, between 1 and band 2, and so on. So let's just put 3 in here. What would the divergence between band 1 and itself be? Same PDF. You're going to have zeros on the major diagonal here. And then the divergence between band 2 and band 1 is going to be some number, d sub 1, 2. And between band 2 and band 1 is going to be d sub 2, 1. And they're going to be the same. Right? So you're going to have a symmetric matrix. So you wind up having to compute this lower triangular or the upper triangular part of this matrix. And that would be all the possible divergences that you can come up with, okay, for these particular, 3 classes in this case. So D13 and 2 to 3. Right? So you'd have to compute those 3 in this case. And obviously, it goes up as you have more and more. All right, now, but what you have, what you have here is 3 numbers. So you're looking at 3 numbers, and the divergence between band 1 and band 2 might be really high, and the divergence between band 1 and 3 might be low, and between 2 and 3 might be low. So is this choice of bands good? Well, it's kind of hard to tell because it depends on which classes you're looking at. And this divergence matrix is really good if you want to find the difference between 2 and 1, and that one happened to be high and all the other ones are low. You can say, well, I don't care. The other ones are low. As long as I separate 1 from 2, I picked a good set of bands. So you can look at this, but in general, people want to solve the problem of how can I do the best image Y across all the classes that I'm interested in. All right? So in that case, we go to this, this concept that we always go back to in, what do they call it, mononumerosis or something like that, where we try and boil it all down to 1 number. All right? You could go ahead and you could figure out the average divergence in that divergence matrix, which would just be the the summation over the rows and the columns, or the upper triangular and lower triangular part of that matrix of the pairwise divergences. And in this case, what we're going to do is multiply them by the a priori probabilities of those classes occurring. Right? So these will be weighting factors based on the number of pixels that you'd expect to see in the scene. Right? Because if the divergence between band 1 and band 2, class 1 and class 2 is very high, but there's only 7 pixels in the entire scene that are class 1 and class 2, well, I don't want to have that weight really heavily into my average divergence. Right? So I would weight it by the a priori probabilities, and that would take the probability, or the weight on that particular divergence, and it would put it very low. Okay? So that's just to keep that, keep small pixels out of the way. You might have a situation where those 7 pixels are the only important ones to you in the entire scene, in which case you could weight by the inverses of those probabilities. And so you could rearrange this, but in general, folks would do it in this manner. All right, so if I wind up with this situation, so let's say, let's generalize this a little bit. If you have m spectral classes that you'd like to classify, right? So I have m total classes that I want to be able to separate, and I have n, big N, total features or bands, right? I call them bands here, but these could be heralded features. Right? You could use these heralded features. You could use spectral bands. You could use principal component bands. Whatever you want, right? Whatever those features want to be, you can include those here. And you wish to pick the best little n feature subset to maximize the separability of these classes. So, how many little n classes do I pick out of big N total to be able to separate these m class types best? Right? That's the problem that we're going to look at. Right? You have to compute all the pairwise probability, or all the pairwise divergences between those classes. So what do you wind up having to do? So there's n choose little n, or big N choose little n, possible combinations of n features from n total. Right? So if I had 10 bands and I went to pick the best 7, 7 choose 10. Oh, I'm sorry, 10 choose 7. I'd have to compute that. And you'd go back to your stats book and look up how to do that particular combinatoric, and it's right down here. So once you figure that out, and that was the hardest part for me, I forgot how to do that. Right? So I looked that up, and then all right, so I have those possible bands to choose, but I also have to take into account my pairwise divergences. So if I want to choose if I have m spectral classes, I need to look at them 2 at a time. So I have m choose 2 pairwise divergences to do. So I have lots of band combinations and lots of pairwise divergences to compute to build up this divergence matrix. Right? So how many divergences do I need to compute? Well, I have to compute the product of those 2. So let's take an example here. If I have Landsat, 7 bands, we'll include the thermal band just for this example. And I want to choose the best 4 out of the 7 bands. And I have a problem where I want to separate 5 different land cover types. Right? So what do I have? I have 7 choose 4 for the possible band subsets that I might want to use. and I have 5 choose 2 divergences that I need to go ahead and compute. So the product of those two come out to be 350 divergence values that I actually need to go ahead and compute. Now you can imagine that number could blow up really quickly and very, very large. Okay? So you need to be, well, you need to solve your problem. Right? So I don't want to say be careful not to choose things that blow up here, but just be aware that the computations involved here, if you go back and you look at this, you got to compute inverses of large matrices perhaps, you have to add them together, you have to compute traces. I mean, this isn't a terribly complicated set of computations to occur, but the more and more bands, the slower and slower it will get. We'll see another one in a second that's much more computationally intensive than this one. But in this case, we'd have 350 to look at. Okay, now, what happens here? Well, this doesn't quite behave exactly like I want it to. Because if you look at this equation, part of this is the difference between the means. Right? So let's say I have, let me go draw this again. Let me say I have a class here. All right? And I have one distribution that falls here and one distribution that falls there. Right? And they're already very well separated from one another. Agreed? Right? You could probably separate them here, right? Using parallel. This is in trouble. Right? You could use a parallel pipette classifier. You could probably do a good job with one man. Now, so my classification accuracy in this case, let's say it actually fell perfectly like this and there was no overlap at all between it. What should my classification accuracy be if I was just using this one band? 100%. Should be 100%, right? All right, now, what happens if I can force this cluster to move further to the right? What happens to my divergence? It increases. Right? So I get an increase in divergence. What happens to my classification accuracy? Still 100%. Right? So I could continue to force these clusters apart by adding more and more bands or choosing different bands, but if my classification accuracy is not going to go up, why do it? Right? So the concept that I want to show you here is that even though the distance between the class means, or as my distance between class means increases, and by distance here I mean either Euclidean distance or statistical distance, if either one of those happens, the probability of correct classification is going to go up and approach 100%. Okay? So the further I move these things apart, the better I'm going. But eventually I start to asymptote and approach 100%. If the distance between the class means is computed using a probability distribution like the Gaussian multivariate normal distribution, then I could continually increase this divergence value as I increase that distance in a quadratic form, right? Because if you go back and you look at this, this is a squared term over here. So I'm going to get a quadratic increase in my divergence as I move further and further apart. As my two means become further separated, this term here is squared, so that divergence value is going to go up quadratic. Right? So this isn't a good behavior, because if I can increase my divergence and I say, hey, the best band set to choose here is the one that makes the greatest divergence, well, I'm going to look for the highest value here. But if this is just going to quadratically keep going up, and this is going to level off, well, I probably could have stopped way back here and got 100% classification accuracy, or pretty close to it. And that might have meant fewer bands. Right? So while this all makes sense, if you believe the derivation that Swing and Davis went through, and that's the final equation, this all makes sense, but it doesn't behave quite the way we want it to. I'd rather see this curve plateau. I'd rather see the divergence, or some measure of separability, I'd rather see it plateau as I increase the distance between classes. And I'd like to see it plateau at the same place where this asymptotically approaches 100%. All right, so along comes Jeffries and Matsushita, and they proposed a distance they call the JM distance, named after them. Okay? And its form, rather than divergence, they call it J sub ij, right? Big J sub ij. And what is it? Well, it's the difference between probabilities, just like we had before in that likelihood ratio. Right? We had a difference between the logs of probabilities. Here we just have the difference between the square root of the probabilities squared. And we do that over all x between two probability distributions for two separate classes. Okay? And that's going to be this measure J sub ij. All right, now, if I go ahead and I plug in the Gaussian multivariate normal distribution for these probabilities, and I go through and I do all my rearrangement and solving, I actually wind up with this really simple equation right here. 2 times 1 to the e minus b, right? Except this is b, all right? So for the multivariate normal distribution, you can see that all the right things are in here. There's the mean vector, there's the covariance matrices, and that's really it, right? That's the only 2 things that are in here. Covariance matrix for class I, covariance matrix for class J, mean vector for class I, mean vector for class J. It comes out to be that form. Now this metric right here is what's known as the Bhattacharya distance in a lot of stats textbooks. So if you look up Bhattacharya distance, you'll see this formula. So it's nothing special that they did here. They just relabeled it. Right? Bhattacharya distance existed for forever. Jeffreys and Matsushita just used it in this form that you have right here. Now, if you look at this function, since you have a negative exponent, negative b in the exponent here, this is going to plateau. So, if I go ahead and I plot, just conceptually, what's going to happen here, Jm distance, if you look at this, 1 minus e to negative b. What happens is negative b gets large. This term goes to 0. And the Jm distance, or Jm distance in this case approaches 2. Right? So what happens is that as that distance between class means starts to increase and that Bhattacharya distance gets large, then the Jm distance asymptotically approaches 2. Okay? And the probability of correct classification also approaches that plateau right around the same point. Right? So this is a much more well-behaved metric because they just rearranged the function so that it would be asymptotic. All right, now, big question to you guys. Why is that 2 there? Anne-Marie's got the right answer. I have no clue why that 2 is there. It's going to approach 1 or it's going to approach 2. Right? So,
Maybe
put the
just
2 in.
spread out the part where, if you go to the next slide, where you're seeing that part where it kind of shifts over, maybe we'll just spread that out more and make it one other different.
Yeah, maybe. I've implemented this both ways with the 1 and 2, and I get exactly the same answers both ways. Lots and lots of data sets that I've run through it. It's just one of those.
There's 2 people making
Yeah, there's 2 people making it, so they each wanted part of it. I always leave the 2 off. When you actually compute Jm distances in NV, the maximum values approach 2. So NV implemented that, but that's just an extra single scalar multiplication that you need to do. It probably doesn't hurt your runtime all that much, but it is one of those things that I don't think is necessary. All right, so Jm distance works out great. All right, so now think about what you could do with this. All right, so now let's say you're choosing your ROIs, just like you've done, hopefully you've done in the lab, right, at this point. And you wanted to say, hey, are my ROIs chosen well? Well, you can go in and between your classes, between 2 ROIs, or between all your ROIs, you can go ahead and you can compute this divergence metric. And you can say, with the current ROIs that I have, am I going to get good separability? So what do you want here? Well, you want an average Jm distance that approaches 2. Okay? If you have an average Jm distance that is about 1, then you're probably not going to get good separation in the quality of your classifier with the bands and the features that you've selected to use. is not going to work all that well. You want to drive that JM distance up to be close to 2, if it's at all possible. All right, so what would you do in that case? Well, you probably go back and pick new ROIs, and then you recompute these distances and see how you do it. Right? That's one way to use it. The other way to use it is I could now go ahead and compute the average JM distance for class 1 and class 2 using bands 3, 7, and 9. And then I can compute the average JM distance for those classes using bands 1, 2, and 4. And I can use every 3-band combination out of Landsat, perhaps. And then I can choose which best 3-band combination to use to do the separation of those classes. Right? So if for some reason I can only use 3 bands out of the 7 for Landsat, and my question to you was which 3 bands should I use? Well, for every band combination, every 3 out of 7 that you can choose, you go ahead and compute an average JM distance between the classes that you're trying to separate, and the greatest one with the largest value, is going to be that 3-band combination to use. So if you remember way back at the start here, our purpose was to do direct elimination of features that do not contribute to the power of the classification scheme. Well, you can interpret that as going ahead and computing this for every set of bands that you want to use. If I had to eliminate 4 out of 7, which best 3 would I pick? This would give you a way to decide that. Okay. You have to have your data in hand to do this. Right? So if you were to want to only send down 3 bands from that orbiter around Mars, you would have to have lots of data sets beforehand to solve this problem. And then you can pick which 3 bands. Right? But you could use it post-fact to pick which best 3 bands for sure. And you can use that to help design your next system. Right? Another way you might use this is, let's say you've been given a blank slate. You're working for NASA, and they say, you know what, the next Landsat's all yours. You can make every design decision for this new system. If you get in that position, right, you got to remember RIT is where you got your graduate degree, and you want to give lots of money back to RIT to help you do that. Right? So if you ever get in that position, we're totally willing to help. Shameless advertisement. Right? So, but if that was your decision, imagine what you could do. You could now say, let's forget about bands altogether. Let's look at spectral signatures. So let me go grab the library from JPL that has thousands of spectral signatures and materials all around the world there. And it's defined on 1 nanometer centers. Right? So I could say, what best 17 reflectance points that represent a 1 nanometer center value would I choose to separate these land cover classes? Which 28 do I choose? Which 400 do I choose? All right, now let me start integrating. Let me start taking 10 nanometer chunks at a time. And if I had 10 nanometer wide bands, which best 10 nanometer wide band would I choose? Which best 20 nanometer wide band would I choose? Which best 40 nanometer wide band would I choose? Let me choose bands so that there's equal signal to noise ratio in them. And there's going to be thousands of combinations that you can do that. Which best would I use? You can imagine writing, a really long-term study to go ahead and best design those features using this kind of approach. I wish people would do that, right? To this point, that's never played into the decision of a satellite design. But if you have that option, a lot of times people say, hey, here's your hardware, go make a satellite. You don't really have a lot of choice. Right? You're limited by the hardware that's provided. But if you ever get a clean slate, and hopefully people will start to think a little bit more smartly about designing satellites rather than just building them and then figuring out what to do with them, which is typically design. If you can start from scratch and just pencil and paper and go through an analysis like this, you can come up with a really hot satellite design to solve your particular set of problems that you're going after. Okay? Using an approach like this. All right, so JM distance is great. All right, but Swain and Davis were not going to be upended. Right? So they came up with what was called transform divergence. All right? What did they do? They took their divergence metric and they put it in a form exactly like the JM distance. So it was asymptotically falling off as divergence increased. Right? But if you look at these two metrics, they have a lot of similarities between them. Right? If you look at this term here, this is distance between two means normalized by variance. You look at this term in the Balkaria distance, what do you got? You got the square distance between two means normalized by the average covariance matrix. Right? So these two terms are very similar to one another. This term, sum of the two covariance matrices determinant of that divided by the determinant of the square root, or square root of the determinant of the individual covariance matrices, natural log. And over here you have the trace of the difference between two covariance matrices divided by the inverses of those same two covariance matrices. Sort of similar to this. So they're not all that much different from one another. So this makes every logical sense. Let's do this. So they went ahead and published that non-saturating divergence term called transform divergence. And if you had to choose which one worked better, it's sort of a hard decision to make because they're so similar to one another to begin with. Which one would you rather compute?
The ones with all the matrices.
What's that?
I'd rather compute this one.
This one. Why?
The other one have all the matrices too, and the V is the exact same V.
Yeah. Oh yeah. This. Oh, I'm sorry. This is the Balkaria distance. This is the same
Ah.
as for JM.
Oh, the
This is divergence. I just wanted to show you both metrics here.
Maybe with the JM, just because it has only one inverse of the matrices.
It has this inverse,
All the
but it
others-
has these determinants. Right. So you got to kind of you have to do a computational study on this to figure out which one is better. And my guess is they're going to come out to be very close. And if you look at the answers that come out whenever you do both of these, they almost always give you the same answer.
And again, the 2 here is magical too.
Because the other guys use two.
Okay.
Yeah. You know? Yeah. Again, no reason. All right. So let's I'm doing this cold. I didn't try this before class. Let's try this real quick in NP.
What's more computationally intensive, inverses or determinants? So both.
Depends on the algorithms that you implement to do them, right? I mean, there's very efficient inverse computations, but that doesn't mean that's what MATLAB implemented when you raise something to the -1, right? So you really have to take the language that you're using and just do a quick study.
But don't you need the determinant when you compute the inverse?
Depends how you compute the inverse. You don't always need the determinant. Gaussian elimination, for instance, doesn't use the determinant. All right, so same image we've been working with. Let's pull up those regions of interest. Okay, so now if we go into the ROI tool, you can see those are the same ROIs that we've been working with all along here. Under options, compute ROI separability. You do that, it asks you which image to get the stats from, which we have open. You choose all, in this case, 6 bands, because the thermal band's not in there. And select the input regions, so let's use all of them. Go ahead and let that compute. Get out here. Okay, so JM and transform divergence. All right, so region of interest name. What do we got? Let me read this. ROI name. What's that? JM transform divergence. Okay, so here's the JM. Here's the transform divergence. JM transform divergence. JM transform divergence. JM transform divergence. So you can see that essentially the same, right? again, essentially the same for bare field. Good here, they're all the same here, they're all the same, and they're all really close to 2, right? We've got 1, 2, 4, 3, at least 3 9s in every case here. So, the pairwise separation test leads to most. What does that say? Golf course, grass. Golf course, grass, 157 points, and bare field. So here's the pairwise divergences. Right? So separating grass from bare field, 1.99. River water from urban, 1.99. Bay water from river water, 1.99. Separation between everything here is really good. So at this point, this is when you try and reach around and pat yourself on the back. This said you did a really good job at picking points. And that's what you want to see. So if you, as you're picking your ROIs, if you every so often go off and do this, you could see which ones are poor. If bay water and river water was 1.2, then I know I probably picked some bad choices for one or the other or both of those class types. So I'd go back and I'd look at those again. But it lets you look at all those possible combinations as you go through this. Now again, for Maria, you mentioned this before class started today. This would have been great to have while you're going through this current lab, because you could have picked better ROIs. But the object of this lab wasn't to do a good classification. That'd be, you know, if you did a good classification, that's awesome. The idea of this lab was to figure out what you did poorly that you didn't get a good classification. If you didn't get a good classification, I think you learn more from that. But this, just definitely keep in mind this tool. So I think this one's a really nice tool to be able to run along with that n-dimensional visualizer, right? Because that you can start to see, hey, that class really blew up and it's all over n space. You would probably think twice about using that ROI in the classifier. So there's a lot of tools that they built in to Envy here to help you out, but you can see they're tools from 1978 publications, right? So there's nothing earth-shattering here. So these are things that you should definitely be using. But I want to say honestly, until these things showed up in Envy, I never used them. You said you've done classifications in the past. Have you ever used these tools? Yeah, I mean, you pick ROIs all day and you classify and you go with that. But exactly, and that's not always a good metric. Does it visually look right? Especially when you're looking for something in a scene that is anomalous.
Seems weird that we're calculating this for like ROIs and then entire bands and then entire other things.
But you can use it so many different ways. That's the key here. What I want you to walk away today is you can use it to evaluate ROIs. You could use it to design a new sensor. You could use it to figure out for a particular application for a sensor that's already built, which bands from that sensor should I use to separate these 7 classes. And you know what, that answer is going to be different if I looked at 5 different classes. So if I was trying to do an agricultural kind of classification, these 3 bands will come out. But if I want to do an urban classification, I would pick a separate set of 3 bands. Right? So there's so many different ways that you can use this sort of analysis. And also keep in mind, if you wind up going outside of remote sensing in your research or in your careers, that this sort of thing can be used in all kinds of fields. Right? Color scientists can use this constantly to figure out, are 2 colors visually or perceptually different from one another? Right? You can use these sorts of approaches. So it's a very powerful set of things. You see it mostly defined in remote sensing literature, but if you go to Swain and Davis, to this book right here, and you look at the references there, it's been in stats books since the beginning of stats, and these things have been around, right? It's just, what do people use them for? Remote sensors really pick them up and use them on a regular basis.
We need popcorn next time.
Yeah, I know. I wish I knew how to use that. All right. Will this be on a test? It could be.
More conceptual than actually plugging numbers.
Here, am I going to ask you to do that computation on the test?
No.
The answer here is probably no.
We'll all leave the test.
Any questions? Everybody here too. Very cool. That's all I got. So, test on Thursday. Like I said, hopefully I'll be here if I make my plane. Monica's on deck in case I'm not, so whatever, it'll be right here. Greg and John, make sure you get to Cindy and let her know when you want to take it. And any other questions that came up while we were going over that? Who's taking the comp this year? Not many. So, like I said, this material doesn't show up on the comp. Some of this material shows up, tends to show up on the comp through image processing. So at least you'll get to see it twice. So you'll have that slight advantage. All right, cool. We'll see you on Thursday then.